David Smith here with another flipped classroom math lesson. A few tips before we start. First, remember that you can speed up or slow down the playback if that helps you follow along. Second, you can turn the captions on and read my words on the screen. Third, you can pause the video at any time to catch up with your notes or write down questions for class. Today's topic, limits that fail to exist. So far, you've been looking at situations where the limit is there. But I think maybe the homework that you did last, there was one problem where there was not a limit. So we're going to take a deeper look at that, okay? So our first function is going to be pretty simple. It's the absolute value of x, and if you need to remember what that is, you put the line brackets around a number. It means absolute value, and it just means the positive. So if you put a negative in there, it's actually, this turns it into the positive number. So absolute value of negative 2 is just 2. Absolute value of negative 4 million is 4 million. The absolute value of 5, well, it's already positive, so it just keeps it positive. That would be 5. So we want to check the limit of absolute value x over x as x approaches 0. And we know there's a problem. We can't just plug 0 in because we'd have 0 in the bottom of a fraction. That's undefined, so we can't do that. So we're going to approach it from both sides and look at the behavior, okay? So I've made my table of values here, and you can see my x's are going from negative 2, negative 1 to 0, and 1, and 2. And now let's plug them into our function and see what we get. So negative 2, absolute value of negative 2 is just positive 2. So this becomes positive 2 over positive 2, or over negative 2. So this is negative 1, okay? And the same thing happens when we plug negative 1 in for x. That turns it positive. This one's still negative. So this one's also negative 1. And you can see the same thing happens, or a similar thing happens over here. If I plug 1 in for x, it just stays 1, and I'm 1 over 1. So instead of a negative result, I get positive. And that's going to be the same. No matter what I plug in for x, the result is going to be positive 1. And see, here's our limit, our 0. We're interested in for our limit, and that's undefined. So we can't evaluate that directly. Now, let's take a look at f of x. Is f of x approaching a number as we get closer to 0 for x? No. And is f of x approaching a certain number as we come from the right side? No. It's negative 1 here constantly, and it's positive 1 here. So there is no limit for when x approaches 0 of absolute value x over x. Now, I want you to pause the video for a sec. I created a coordinate plane here. I want to graph this function and show you how it looks on the graph. You could pull Desmos out if you want to do it on Desmos, but just get this function graphed. Okay, so you'll see that no matter what the x values are, as we're approaching from the left, it's negative 1. So this goes like this, but then we draw our circle around the negative 1, around x being 0, because we can't do that. And it's similar over here. You draw an open circle there, and that's our function. So it goes that way and that way. And the open circles indicate that we can't actually evaluate it when x is 0. It also shows that this function is discontinuous. Okay? Okay, let's look at another one. Here's an interesting function. Same problem though, right? As x approaches 0, we're looking for the limit of 1 over x squared. We can't plug 0 in because we end up with division by 0. And I noted that on my table. Here's my x. 0, and I've got undefined for that. So let's approach 0 from each side and take a look. So when x is negative 1, the f of x is going to be 1. And you can verify these either on your calculator, or you can go into Desmos and put this function in there, generate a table, do all those little tricks that you can do. So when f of x, or when x is negative 0.1, f of x is going to be 100. When it's negative 0.01, f of x is 10,000. I just wrote 10k for 10,000. 0 undefined. And then since we're squaring, these numbers are going to be mirror images of each other because they get turned positive. So when x is 0.01, f of x is 10,000. When it's 0.1, f of x is 100. And when it's 1, f of x is 1. So you can see from our table that we're not approaching any number. We're just getting bigger and bigger and bigger. If you did 0.001, this number is going to get even bigger and bigger and bigger. For a limit to exist, we have to approach a value from both sides. So this one is definitely not doing that. There's no limit for this one. Take a minute, see if you can just sketch the graph. I know you can put it in Desmos and we'll show you the graph, but this graph should be pretty easy to see. I didn't put units on there, just do a quick sketch, see what you get. Okay, here's what this graph looks like. Something like that. As x gets closer and closer to 0 from either side, f of x is just getting bigger and bigger and bigger. So this is a graph for that function. Okay, another place where limits fail to exist involves oscillating behavior. So these are functions that will bounce around between two values. So if you recall, when we played with trigonometric functions, mostly cosine and sine, the very simple f of x equals sine x, that one bounces between 1 and -1. It just goes up and down and up and down. So that function has no limit. It doesn't work that way. So what I want you to take a look at is this function. The limit as x approaches 0 of sine x. Notice how we can't put 0 in for this, so we can't evaluate it directly because that would be undefined, and you can't do the sine of something that's undefined. So take a moment, pop open Desmos if you want, see if you can figure out and see why there's no limit for this function. So if you put that into Desmos, you got something like this. And you can zoom in or out on it, and it doesn't give you any more resolution. What happens is as x approaches -1 or as x approaches 1 or approaches 0 from the negative side or from the positive side, you're going to get this oscillation. And no matter how finely you go in there, you're going to still see that the f of x is bouncing back and forth between 1 and -1. So there's no limit for this function. It fails to exist. Okay, let's review what we've gone over so far. So first off, remember our notation. The limit of f of x as x approaches c is L. Now, for these problems, there is no L. There's no limit. Okay, so three cases that we looked at. The limit does not exist when x approaches c when f of x approaches a different number from the left as from the right as x approaches c. So that was that first example we did. They did not approach the same number. Second one, when f of x increases or decreases without bound as x approaches c. So that was that second one where it just kept growing and growing and growing as we get closer and closer to x equal to 0. So no limit for that problem. The last one was when f of x oscillates between two values as x approaches c. So those are the three cases that we've studied here that talk about when limits fail to exist. Okay, one more bonus topic. Woo! Actually, this is something you've probably sussed out on your own already. In some cases, we can evaluate a limit by this process called direct substitution. And it's what it sounds like. You just plug the value that you're looking for x into the function and it will give you the limit. Okay? So in this case, we're looking at the limit of x squared as x approaches 2. So I can plug 2 in for x. I don't get any undefined problems. So that's just going to be 4. As x approaches 2, f of x approaches 4. Okay? Pretty straightforward. So try this one. The limit as x approaches 4 of x squared plus 2x minus 6 over x minus 1. And take a minute before we start. We can do this. As x approaches 4, the bottom of this fraction doesn't get to 0, so we can just plug in. So go ahead, pause the video, plug in 4 for that, see what you get. Okay, this ends up being 18 over 3, which equals 6. So the limit as x approaches 4 of this function is 6. Now that you've finished the video, take a moment and jot down some notes or questions for our next class. Remember that you can also watch the video again if you want to increase your understanding. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.